Thank you for clicking this video and watching a video regarding a line broadening mechanisms regarding our laser physics course. So what this lecture is about, first of all, of course, it will continue what we already started in the previous lecture. And now we will be talking more about the kind of concepts of different kind of line broadening mechanisms to take place. And then finally, with this kind of conceptual lecture, we'll be providing an example in the upcoming lecture regarding saturation and gain of a kind of real phenomena that takes place due to these different kind of line broadening mechanisms that take place and really that affects how lasers behave. So essentially we'll be talking about a spectral hole burning phenomena in the upcoming video, but that's the kind of like in the future. Right now we will basically just go through the different line broadening mechanisms, mainly introduce to you homogeneous and inhomogeneous line broadening. So now let's get started. What we will do here is that we will discuss what kind of effects affect the line shapes and line widths of atomic transitions. And of course, proper distinctions between different types of lasers out there and what kind of lasing media are there. It's really beyond our course. This is kind of like introductory course on understanding the physics, how lasing takes place, how lasers are being built, and so forth. We do note that there are other resonances than just atomic transitions. So for example, a kind of prime example coming to my mind would be quantum dots and quantum wells in semiconducting materials. So essentially like how we can have a semiconductor, for example, lace, how we can make semiconductor lasers. That is a huge industry these days. So there are other than just atomic transitions, but conceptually it's just easier to consider atomic transitions within our treatment. And if you're already familiar with the basics of solid state physics or condensed matter physics, I should also point you that it's really worth recalling the band structure theory underneath solids. So what happens for electronic states when we are putting things into a crystalline lattices. So that's also kind of like a good thing to remember here, that it's not really a kind of like amorphous medium of interest, for example, gas, lasers, and so forth. But many times we also must understand that our gain materials, emitters, are within a crystalline lattice of a dielectric material, such as, for example, a sapphire or YAG crystal or so forth. Okay, so what we do here is that we can really distinguish between two main different types of broadening mechanisms. So this is kind of like a way for us to introduce the kind of terminology here. So there are homogeneous broadening mechanisms and there are also inhomogeneous broadening mechanisms. So these are kind of like two types of categories of what kind of broadening we may have. And this lecture is mainly about these two different mechanisms and what are their similarities, how they connect to the big picture, and how they are different from each other. So we speak of homogeneous broadening when all the atoms forming the active medium or whatever are the kind of like emitters, really need to be atoms, could be something else, when these contribute identically into the process, into the absorption and subsequently into the stimulated emission processes. In this case, all atoms possess the same line shape function, denoted with GH, H as in homogeneous, that is centered over the same transition frequency of omega naught. And in this case, we can just simply write for how many atoms, how many emitters we have, that the line shape function, homogeneous absorption line shape function is basically that of a single atom. And we can write it simply in this kind of familiar way we have already written here. And here the GH, instead of a delta function, this is actually something else. And the simplest case of homogeneous broadening, this homogeneous broadening line function is of a form of a Lorentzian line shape. So we have 4 over delta omega naught. That's the kind of like a width of our line shape function. And then we have these kind of parameters or this kind of fraction here, 1 over 1 plus 2 over delta omega naught times omega minus omega squared. So this is essentially it's a Lorentzian line shape function. And here this delta omega naught is essentially proportional it's equal to the 1 over tau c. Tau c is basically the characteristic time for this kind of process. For example, to spontaneously emit, the excited state to spontaneously emit, and this is really determined by the specific process in question. So here, this basically is the kind of like crucial parameter that we should look at in the microscopic description. That kind of like how easy it is this excited state to relax, or how difficult it is to relax. And already I guess we know from the kind of recalling what we discovered about the Fermi's golden rule, we see that all of this dynamics, how easy or how difficult, how quick the system relaxes, boils down into the quantum mechanics, that how easy or difficult it is for this system to relax or transfer into a different state. What then creates homogeneous broadening? There are different mechanisms, and first of all, there is a natural broadening mechanism. So homogeneous broadening really results from the fact that we do have a finite lifetime in the excited state of an atom, and we know that this is essentially could be calculated by applying the Fermi's golden rule for the situation, and this occurs due to spontaneous emission taking place. And there's really no way of getting rid of natural broadening as a broadening mechanisms. It's always there due to the fact that we always have spontaneous emission from within our system. So if this NE, that's the population of the excited state, decays with a characteristic time of tau SB related to the spontaneous emission, then we can write the dynamics of this population, that it's the population at the origin of time, t equals 0, and then we have this exponentially decaying function of population. So that's how things just spontaneously relax. Now, the electric field or the optical field associated to the spontaneous emission of a photon is then of a form that we have the E, function of t, time, and then we have the original field value, and then we have this kind of like spontaneous decay, and then we have oscillation at that frequency of omega naught. And then subsequently, we can just calculate the spectrum of this emitted light distribution. That's essentially a Fourier transformation of this, and this is our means of calculating what is the homogeneous line broadening due to the fact of natural broadening. So essentially, like we could measure how a system spontaneously relaxes from the excited state into the ground state. We could measure the spectrum, or we could measure the kind of like time temporal dynamics or decay, and then we could be able to Fourier transform and get this line shape function. Or similarly, like if you would have a high resolution spectrometer, we could just directly measure this as an outcome of our experiment. So that would be basically kind of like a means of estimating what is the natural broadening, how much it affects the laser transition line width. Then we have other processes. Another example is a collision broadening. What happens here, and this is really dominant when we are looking at kind of liquids and gases, the atoms may collide within each other. And this is really, as like said, in gases or liquids, or in other quasi-particles. So for example, this may also take place and broaden systems when we are dealing with lattice vibrations, so phonons. So that would be the kind of like solid state material. So this is like a mechanism that just doesn't take place only in gases or in liquids. It takes place also everywhere. And what happens is that when we have these collisions taking place, they induce a random phase jumps into the atomic dipoles. And in the Markovian approximation, so basically the system behavior only is assumed to depend on the current state and not of its past. So then we are also associated with another characteristic time, now labeled as time call, kind of like a collision-induced broadening. And these collisions, they cause the atoms to interact only coherently within the electromagnetic field within this time frame of tau collective or collision time window. So now this is basically another broadening mechanisms that give rise to a kind of broadening of the laser line width. So like we have collisions within the material, and that can be either like if you're treating gaseous medium, they can really be that the emitters, they are hitting each other, and the same thing applies for liquids. But in the case of a solid gain medium, we can have lattice vibrations, so essentially phonons are moving within the solid, and these phonons are hitting electrons, our atomic emitters, and they are giving rise to these kind of broadening via collisions. So this collision dynamics is being basically dictated by this characteristic time of collision characteristic time, and then this gives rise to kind of like fact that we are losing coherence like after these kind of time windows have been passed. And then we have a third process for giving rise to giving rise to broadening of our line width, and that would be the non-radiative decay. So there are also sometimes non-radiative decay channels that affect the atom, and they can also induce homogeneous broadening mechanism. And then the characteristic time would be labeled as NR, non-radiative, and that's the kind of like final broadening mechanism we consider. In general, what happens, like the characteristic time of the total homogeneous broadening, or the kind of like equivalent of a full width half maximum of the line shape function, is really dictated by all these processes we just introduced. So essentially, like it's determined by the sum of the inverse lifetimes of all these contributions. So essentially, the line width, the homogeneous line width, the broadened line width is given by a kind of like inverse of the total characteristic time, and that can be written as a kind of inverse sum of all these different contributions, like this. So essentially, now this tells to us that if we would want to narrow down the laser transition, we should really try to kind of like take into account all these different possible processes and see what we could do in terms of minimizing their effect into the actual line shape. So we could try to, for example, minimize the spontaneous emission. We could try to minimize the collisions taking place within the atoms or within phonons, or we could try to minimize these kind of possible non-radiative channels. So for example, like we might be able to wanting to make a more pure material so that we wouldn't have some kind of defects at atoms, giving rise to a kind of more complicated relaxation channels that are not really radiative anymore, in the sense that we are creating light that oscillates at the laser transition frequency, but rather oscillates at some different frequency. So that's the kind of meaning for non-radiative decay channels. Now let's start looking into the inhomogeneous broadening and ask a question: what creates inhomogeneous broadening in our material? And of course, physically, what happens is that now our atoms, or whatever emitters, absorbers we have, they contribute differently to the overall absorption and emission of light. So this is basically what happens. In this case, the transition frequencies of the atoms that form the overall active medium, the gain medium, the macroscopic medium of interest, consisting of millions of atomic emitters. These transition frequencies, they really vary from atom to atom, so that the transition frequencies omega naught prime are really distributed around a mean value of omega naught with a distribution of G star, and that's the kind of like different line broadening function. And this is known as the inhomogeneous line shape function. So physically, what happens, we have, again, similarly to the case of homogeneously broadened material, we have many atoms, but now different atoms, they interact differently with the incident light, and that gives rise to a fact that we have a distribution of a little bit different line shapes within the material, depending on the atom hitting or like being hit by incident field. So each atom still exhibits homogeneous broadening. So we cannot really get rid of, for example, processes such as spontaneous emission. That's always present within the material. So please remember that. So we always have homogeneous broadening within our material. So what happens when we also have inhomogeneous broadening taking place? We must consider both of these effects. So essentially then the total line shape function G tot is given by a kind of convolution over different frequencies. So we have the inhomogeneous broadening line function, and then we also have the homogeneous broadening line function. And essentially this is like a kind of like convolution, so that we kind of like a sum over all these different contributions together to get the overall total line shape function. Interestingly, if one of the two mechanisms really dominate over the other, then we can really simplify the line shape function. So then only the kind of like block line shape function looks of the form of the dominating mechanism. So this is, for example, often the case that the kind of homogeneous broadening visibly doesn't really show up, although it really affects conceptually what happens. But physically, the line shape function looks of just the inhomogeneously broadened line shape function. Let's consider an example so that we can hopefully exemplify what we are saying here. So let's consider example of inhomogeneous broadening, and we assume that the line width of the inhomogeneously broadened medium is really larger than the broadening of the line width due to homogeneous broadening mechanisms. So basically, this means that then the homogeneous line broadening a line width function GH is approximately a delta function peaking when the omega minus omega naught equals capital omega. Now we can write the total line function G tot as an integral, and like before, this is the integral that we had, and now we are replacing the original homogeneous line shape function with a delta function, and of course this delta function picks out a specific frequency, and we are only dealing then afterwards with the inhomogeneously broadened line function G star centered at this frequency. So this is what happens mathematically if we can simplify things. And of course, not always, we don't really take this kind of extreme limiting case. Most of the time, the homogeneous broadening is really quite narrow compared to the inhomogeneously broadening. So this is usually the case that we kind of when we want to understand the line shape of our laser transition, it's enough to consider only the kind of overall inhomogeneous broadening mechanisms, and that's it. But of course, we don't really see all the effects when we don't really recall that we do have homogeneous broadening. So please, be noted that there is some subtlety regarding also homogeneous broadening. But more on those subtleties later words in different lectures. Okay, so let's now continue looking at the above equation. We see that the inhomogeneous broadening really clearly dominates the formation of the line shape, as I already said, and the line width. So this is kind of example showing what can happen or how we can simplify our treatments. Now the question is, what are the kind of phenomena or processes that in practice give rise to inhomogeneous broadening? First of all, of course, inhomogeneity in the local electric field can give rise to inhomogeneous broadening. So this is especially important in solids and in liquids. And if you have taken a course on solid state physics, please recall, for example, that the local field effects take place in crystalline solids. And because we do have defects and different kind of regions, then these local fields can very sensitively depend on where our atom actually is residing within that crystalline lattice. And that really dictates that how it can also emit radiation and absorb radiation. The same thing applies for liquids. So we do have this kind of a inhomogeneity within the local electric fields, and that gives rise to changes in the line broadening. Another, and this is kind of a very a great, practical, easily understood example, we may consider Doppler effects, and this is particularly relevant for gases or liquids. But I guess this is kind of easy example to understand what gives rise to inhomogeneous broadening, because we already have covered Doppler effect in high school physics, and we can understand that in gases we have atoms moving at different velocities in different directions, and then thus, of course, the kind of like a resonance frequencies of these atomic emitters and absorbers is being dictated also about their, with respect to their relative velocities. The local field effects, and I guess this is something we will be really treating more during our discussions on campus. Local field effects are extremely important in practice when we are looking at solid state lasers. And the kind of like a prime example I'm thinking is that we can, for example, consider titanium sapphire lasers. And these are amazing light sources, amazing lasers, because they have an insanely broad tuning range. The Ti sapphires, we can have them lace within the wavelength range of 700 nanometers to all the way up to 1,100 nanometers. So that basically is the kind of broadest tuning range we can have in a kind of normal laser, not resorting into nonlinear optics. So this is a kind of like prime example that local field effects are an extremely important in our treatment. And why Ti sapphire lasers are such unique lasers? It arises due to the fact that they really have unique local field effects taking place within that sapphire medium into which we have been placing these titanium dopants. And this local field environment really affects the properties of the titanium atoms that act as the gain medium residing, and that's kind of like what gives rise to this broad tuning range. So sapphire, like a alpha aluminum oxide, is really a kind of like a very unique host material due to the fact that the titania have a very specific local field environment. And this is, for example, should be compared against amorphous aluminum oxide, also known as alumina. Don't confuse against aluminum. They are totally different kind of substances, totally different materials. Amorphous aluminum oxide doesn't exhibit the same properties at all than what the crystalline sapphire does in terms of its local fields and how it acts as a laser. But more like as a laser when we dope it with titanium. But more on this really on the discussions, because this is a kind of like extremely nice example of the importance of local field effects. And on the other hand, of the kind of like a kind of real engineering challenges that we cannot really do that much to really change how nature behaves. So that we need to be very smart when we want to kind of advance things. Okay, let's consider Doppler broadening in more detail, because this is a kind of prime example to understand inhomogeneous line broadening. So Doppler broadening takes place in a gaseous medium due to the fact that the velocity distribution of atoms or molecules, please recall the Maxwell-Boltzmann speed distribution, is kind of affecting the resonance transitions of these atoms or molecules. And let's now consider an electromagnetic impinging field propagating within the gas composed of atoms moving at a different velocity v. And now what happens is that the Doppler effect really shifts these resonance frequencies of moving particles in a way given by this equation. So the new resonance frequency omega prime is given by the original resonance frequency times 1 minus v per c, speed of light. So this is how we get broadening due to the fact that the gases are moving with different speeds with respect to a kind of like a still atom. Now, incident light oscillating at the frequency omega is being absorbed only if it hits exactly this changed frequency omega prime. So this is what happens, so that we can write that the omega equals omega naught divided by 1 minus v over c, where v varies between particles, atoms. So we can show that this gives rise to a Gaussian line shape function. I don't go into the derivation, but you can find it from the Svelto's book, so that the kind of like inhomogeneous line width due to Doppler effect is of this form. So 2 divided by the delta omega naught star times natural logarithm of 2 divided by pi this squared, and then we have an exponential term looking like a kind of Gaussian function, and then we have a logarithm of 2n again there. And this delta omega naught star is given by 2 times omega naught times 2 times kpt ln2 divided by m capital M c squared. And this is squared. So essentially here the capital M is the mass of our atom, Kp is the Boltzmann's constant, and this logarithm of 2 is due to the fact that we have defined this line width delta omega naught star as the full width half maximum and not by the 1 over e value. So this is how the line shape function now looks like. Basically, it looks like a kind of Gaussian function, and this line width is being dictated by the temperature of our system and of course, by the properties of the gas. So this is some way of understanding how we can have inhomogeneous broadening within a gas medium just due to the fact that we have a velocity associated with the gas molecules and we can relate this with the temperature. So of course, we can instantly see by looking at this equation that we could adjust things by moving into a different gas substance, or more relevantly, we can improve things by going into smaller and smaller temperatures. But that can be problematic when we are putting things into the extreme. But this was basically all I wanted to say about line broadening mechanisms. I hope I have introduced you the kind of basics, what happens, and after this you remember that there are the kind of like 2 categories. We do have this homogeneous line broadening that we cannot really avoid at all. And then on top of that, most of the time, we also have inhomogeneous line broadening mechanisms that kind of further smear our laser transition. And in the upcoming lecture, we will be showing a kind of practical example that what happens when we do have both of these kind of processes or when we only have homogeneous broadening. So please follow me quickly looking at the kind of and listening for the next lecture. But thank you for your time and patience, and please stay tuned regarding our lectures on laser physics. Thanks, and bye-bye.